if we have the question is if we want to rise a body, the mass is 500 kilogram, and the error rate will be the 1 minute 20 meter. So what would be the power required? So power will be the how many work we need to do in 1 second. So the work done in 1 second will be the mgh. So h will be the mg. You need to get what is the height. In the problem, it tell us the height is the 20 meter over a minute. So we can transfer become what is the 1 second. So the 1 second will be the 20 over 6. Okay, so 1 second it will be 1 over 3 meter. So we get h. So mgh will be the work done in 1 second. So you can understand that work done in 1 second, it will be the power. So the power will be the 163. And then we will talk about how to derive the equation by the energy master. We already introduced the master, the Newton's second law. And by the energy master, it is the other kind of master. For a complex system, sometimes the energy master will be much easier to derive the governing equation for some very complicated system. So the main idea is the change in the total range should be equal to the net work done on the system by the external force. So if we don't have any external force, of course the change of the kinetic energy and also the total change of the energy, it will be here, it will be the kinetic energy and the potential energy. Change of the kinetic energy and the potential energy summation should be equal to the total the work done by the external force. And so the kinetic energy for this system will be the 1 over 2 mx dot power 2. For the potential energy will be the 1 over 2 kx power 2. Okay, so if we don't have any external force, we don't have any external energy enter to this system, like this one, we don't have any force applied on it, then it means the delta omega should be, or delta W should be equal to 0. Then it means the change of the kinetic energy and plus the potential energy should be equal to 0. Okay, so it also means the kinetic energy plus the potential energy should be constant. So according to this rule, our kinetic energy plus the potential energy should be equal to constant. And when we do the derivative for the this t plus u, because the delta u, because the change of the energy should be equal to 0, so derivative for t plus the kinetic energy plus potential energy should be equal to 0. So when we do the derivative for these terms, it will be the m x dot and then x double dot. This will be kx and x dot equal to 0. We can extract x dot here. So when we cancel extract, remove x dot, we will get mx double dot plus kx equal to 0. So this will be our governing equation. It is identical So this is the element mass. We already know how to derive the Gamma equation for this system before, and so assume in the if we use other energy master, assume the k, the displacement, the deflections equal to the mg, and so we can know the potential energy for the u0 here. If your position is here in the equilibrium position, the potential energy should be the mg x0 from the gravity turn. Okay, and we also have the potential energy from the spring turn. It will be 1 over 2 k, the displacement power 2, the deflection of the spring. And so we can imagine that if we have certain displacement in x moving forward, our potential energy will be the mg x0 minus x, and our spring turn, because it will be elongated, so the the spring potential energy will be increased. It will be 1 over 2 k deflection plus x power 2, and this will be the mg x0 minus mg x, 1 over 2 k displacement deflection power 2 k deflection x plus 1 over 2 k x2, and then we can try to get x together, move this turn and this turn together to here, the other turn the same turn here, because mg equal to k displacement, the deflection, so this turn will disappear. Okay, and we also know u0 is this turn. This turn will be just this turn, just this part. So the potential energy will be the u equal to u0 plus 1 over 2 k x2, and the u0 will be certain constant term. So it tells us when we have any displacement, you just need to consider about the potential energy from the spring. You don't need to consider any potential energy from the gravity turn. Okay, so after we get the potential energy, and we can know our kinetic energy will be the 1 over 2 m x dot power 2 plus u0 plus 1 over 2 kx power 2 should be equal to constant, because this systems we don't have any external force. The delta t plus delta u should be 0. So it means the kinetic energy plus the potential energy should be constant value. And when we do the differentiate, it should be equal to 0, because we don't have any change in the total of the kinetic energy plus the potential energy. So this part will be the m x dot x double dot this term after differentiate by the dt, and this part will be the k as x dot equal to 0. So we will get the mx dot plus kx equal to 0. Okay, so we use the energy method to get this equation. And this example is a really good example to let you understand. This system, we have a translation system, coordination system, and also a rotation system. So if you want to use the Newton's second law, you will find it will be very complex. But if we use the energy method, this problem become much easier. You can see the kinetic energy will be from this mass. We will have the translation and also the rotation kinetic energy. So it will be the 1 over 2 mx dot power 2 plus 1 over 2 j theta dot power 2. And our potential energy will be just from the spring, so it will be the 1 over 2 kx2. And we don't have any external force. So T plus U should be equal to the constant. And this will be the whole term. And we can know the x, the translation here should be equal to R multiply theta. Okay? And J will be equal to 1 over 2 mr2 because it is a cylinder. So we can replace the J and theta dot become the x dot over r. Okay, so this part will become the replace the J become the 1 over 2 mr2, and then replace the theta dot become the x dot over r. So we will get x dot power 2 over r2 here, and this will be the same term. So we try to replace all of the rotation system parameter become the translation system parameter. You can see we replace the j become m, theta become x. So we will get the translation system solution, the coordination system x, the solution for the x. So this should be equal to constant, and when we do the differentiate, you will get the m x double dot plus 3 to kx equal to 0 will be our solution for the translation systems. But for the rotation system, if you want to get a rotation system, you just try to replace all of the translation system become the rotation system parameter. We can replace the x dot become r theta dot, and x become r theta. Then we can get the translation system. So when we get the translation system solution, and we replace x equal to r theta and x dot equal to r theta dot, then we will get our solution will be this one. And when we see this one, we can know what would be what will be our oscillation, our natural frequency of for the vibration, and our natural frequency will be just this term, square root of the 2k over 3m. And if we want to define, we already know the natural frequency omega will be the square root k over m. And we can also use the energy method to get these conclusions. So assume our system will be oscillate. So if it will be oscillate, the x displacement should be the a multiply the sine omega t. Assume it will be oscillate, and we will have certain amplitude a and a certain oscillation frequency. We call it natural frequency omega. And we want to know what is the omega related to what kind of function. So if x equal to this one, our kinetic energy should be follow this equation. Okay, and because this is s dot will be the a omega cosine omega t. Okay, so and the power 2, so it will become this term. And the kx will be directly assigned, x directly assigned here, so we get 1 over 2 ka2 sine omega t2. And when the maximum value for the kinetic energy and the potential energy should be equal. Okay, so we will say the T maxima should be this term. and it will be because this maxima is 1, and for the potential energy will be this is 1, so it will be also this term. So when it should be equal, so this item should equal to this item, then we can get this form. So we can cancel A2, and we will got omega 2 equal to K over M. Omega equal to square root K over M. So use the energy method, we can also derive what is our natural frequency. And then we will talk about some parallel and the serial spring. The parallel, when we have two parallel spring like this way, K1 and K2, what will be the equivalent stiffness? The equivalent stiffness actually will be identical to the direct summation. And how do we prove it? Because K1x plus K2x should be equal to F. So we can, and the F we can assume we have only one spring here, equivalent spring. The equivalent spring multiply the X, also the displacement, should equal F should equal to K equivalent multiply X. So we can get the K equivalent actually equal to K1 multiply K1 plus K2. So if we have two parallel spring, the equivalent stiffness spring constant should be direct summation the K1, the parallel to the two parallel spring constant K1 plus K2. So if we have a serial spring, what happen here? So you can see it is a serial spring. When I apply force here, the force will be in the K1, K2, we will also still have the same force. So F should equal to K1 delta X. Okay, and K2 equal to K2 delta X2. It should equal to K, assume we only have one spring here. So K equivalent plus the total displacement X delta X1 plus delta X2. So according to this equation, we can replace the delta X1 become the F over K1 and delta X2 become F over K2 and put inside, put here, this put here, this put here. So we will get F actually equal to F K equivalent over multiply F over K1 plus F over K2. Then we can cancel the F, so it becomes K and divide this total to the left side. So this power become K equivalent should be equal to F already cancel become 1. 1 over this whole term, 1 over K1 plus 1 over K2 equal to K, so it will be K1 multiply K2 over K1 plus K2. Okay, so what would be, if we have 3 serial spring, what is the answer? If we have 3 serial spring, K1, K2, K3, and a force. Actually, I try to remember this equation, not this conclusion, because this is must be the most easy to remember. If I have 3 elements, my K equivalent should be equal to the 1 over K1 plus 1 over K2 plus 1 over K3. It should be equal to this one. And after the simplification, you can get the solution. Okay? So this will be the other example. If I choose this point, assign the force, and this part is ground, this part is also ground. It is not serial. It is actually it is like parallel. You can see K1. This is identical to parallel. I have F, and the K2 also connect to the ground. Do you understand? I just move the ground. So if we have a system like this one, how do we calculate the equivalent stiffness? So according to this part, I will try to calculate this part. This part will be 1 over K2 plus 1 over K3. Okay? And this part and this whole part should be direct summation. So it should be plus K1. So this will be the K equivalent. So after certain simplification, you can get the solution. So the same rule when we have the damper turn, actually we apply the same rule. So if we have two parallel damper turn, the total damper will be the B1 plus B2. If we have a serial, it will be the 1 over V1 plus 1 over V2. So we'll get this one. So for the damper turn, it will be identical to the rule will be identical to the spring turn. Okay, but sometimes the rule may be changed in other system, like in the electrical system. So this rule is only applied in the mechanical systems. For the resistors, it may be total difference. It may be inverse. The serial will be summation, and the parallel will be apply this equation. So in this rule, it is not always this kind of rule. Sometimes it will change. Okay, so for the damper turn and spring turn, you just follow this rule. The parallel item you should do the summation. The serial you will use the 1 over inverse of 1 over B1 plus 1 over B2. Okay. What would be the equivalent damper turn here? So I will try to get this one. So this one will be because they are parallel, B2 plus B3. And this one and this one, these two will be the serial. So my solution will be this is B1. So the final solution will be 1 over B1 plus 1 over this whole term is B2 plus B3. So this is the equivalent damper turn. And if we have this kind of system, what will be our equivalent spring? So you can see this one and this one is the parallel, but this one actually also parallel. You can move the ground to the upper, so it will be the equivalent spring constant actually will be the K1 plus K2 plus K3, and then it will be KEQ. Okay, so if we have the KEQ, what will be our natural frequency? Natural frequency, the equation will be omega equal to KEQ over M. So this will be it will be the K1 plus K. So if we this is the problem. If we want to model a system like these rotation systems, So we have an input. The input will be the theta input theta I. The output, and after a spring, we connect to a mass. We have a moment of inertia, and we also have a damper. It will be fixed on the ground. Okay, then so this means it will fix on the ground. So then we will have the output theta O. So how do we model our systems? So apply the rule I teach to you. This should be very easy. So what will be our free body? Our free body will be this one. And then what will be a system? Theta J, theta O will be our free body coordination system. So you will use the J theta O double dot plus J plus not J B theta O dot plus K theta O minus this coordinate you select minus other coordinate theta I then equal to 0. So we get if our we have equation. A system like this okay, one, so it is kind of and you should understand how do we derive the Gamma equation. It is the actually it will be the parallel spring and also parallel temperature. So we actually directly get the gamma it is this system actually is identical to the K1 K2 B1 B2 and the mass. So if I have this, how do we derive the Gamma equation? It will be the mx double dot plus K1 plus K2 will be the equivalent stiffness multiply the x, the coordinate I choose, the body, the free body I choose, and the coordinate. And the identical temperature will be the B1, B2 equivalent then temperature. So this will be x dot equal to 0. So it is also very easy to derive the Gamma equation. So if we want to, we have a more complex problem here. If we have a pendulum system look like this one, we have a ball and we have a cable, and then it will be swing, oscillate, and then this will be the length L. And so if we use the Newton's second law in the rotation system, we treat like this is the pivot point. So and so what will be our if we treat like this is pivot point, what will be our moment of inertia here? It will be J, and the J will be actually will be equal to the apply the equation, apply the parallel theory. If this is we treat like this ball is just a point, not actually a ball, it will be a point. Okay, so it will be the m L power 2. Apply the parallel theory. Okay, and so we can get the, and we will also have a moment, a torque generate due to the gravity turn here. So mg multiply the moment on mg. So the mg multiply the moment on L, it will be the L. L is here. L sine theta, it will be our moment on. L sine theta will be our moment on. So it will be here. So we will we can get the, if we say the So we can get the as we apply we can get the J, apply the Newton's second law. It tell us that J theta dot should be double dot should be equal to total external torque, and the external torque will be here due to the gravity turn. Okay, so the external turn here will be this just follow this turn. If we assume the this direction is positive, so this direction should be negative. So we will get the negative mgl sine theta here, and we can try to so our replace the j become this term here, and we can cancel the m, and for a very small theta, sine theta actually equal to can be approximate to theta. So this term we can replace as theta. So our equation can simplify, become and remove the m, L, 1L. So it will become the theta double dot plus g over L theta equal to 0. So when we see this equation, what will be our oscillation frequency? It will be the g L square root, because remember our equation will be the k over m, and the k here will be identical to this term g over L, and m here will be 1. So it will be a g over L square root. So if you know the length, actually you can directly know what is the oscillation frequency. Okay, so this is we use the Newton's second law to apply the equation to get the governing equation. So if we use the energy method, how do we get the equation? So what is the energy for this systems? The energy, the potential, we only have the potential energy. Potential energy will be the mgh, and the other one will be the rotation energy, the rotation kinetic energy. So it will be the 1 over 2j angular acceleration power 2. Okay, so what will be our h? So if I assume the here is the, let's see, assume this whole term is the L. This one actually should be, and then L O L and cosine this term. This part will be the L cosine theta. Okay. So the height, if I so the height here, if I assume the height here should be the L minus this height. Okay, so if I assume this part is the potential energy is 0, so this height, the potential energy will be mgh in this position, and this height should be the L, this part is L minus L cosine theta. So we will get mgl minus L cosine theta, and plus the 1 over 2 we already know the moment of inertia is the mL2, and the angular velocity power 2 should be equal to constant. Then we can do the derivative. So this derivative we can get mg L is actually it is the constant term, so it will disappear. And the second part here, cosine theta, mg L cosine theta, do the derivative will be mg, it will be negative, but after the differentiate, the negative cosine will become sine, okay? So it will be the mg L sine theta multiply the theta dt, so it will be omega. And then this part, it will be the m L2 and alpha, and then this part is something wrong here. This is not alpha, this is, should be the omega. This is omega. I will modify, I will correct the name. So if this is omega, this will become mL2 omega multiply alpha. So when we try to reduce the so we can cancel the center, m can cancel, and L, certain L can cancel. So it will become this term. And if we try to let the sine theta equal to theta, it will be direct. And then this is the other example, the form we generate. So if we have a system look like this one, so if we use the energy method, I feel it's much easier sometimes. So for a rotation system, it is a pendular system, but we also have the other two force from the spring. So the first part here, it will be the same. I think you already know this part. The other part is what is this term, the torque from the two spring. So you can see when we have a rotation angle, what will be the displacement here? The displacement here actually will be the A multiply the sine theta, and this part should be the A multiply cosine theta. Okay, so so you can understand our moment on will be the A cosine theta, and the force, this force should be the K, because we have a displacement. We put this part is elongation and this part is place, but the force will be go both of the direction. If it is a parallel systems, so it's identical to parallel systems. So our equivalent stiffness 2K, and we have a force. We will generate a force for go to this direction. Go to this direction. Okay, and the force, it will be related to the K multiply A sine theta. It will be the force due to the compression and the elongation for the spring turn. So it will be the 2K A sine theta. This is the actual force. And the A cosine theta will be the moment on. So we will generate a negative because it will rotate this direction. If we assume this direction is positive, so this direction is negative force, negative torque. So we will get negative 2 Ka sine theta A cosine theta. Okay, after we get the So we almost get the governing equation. The other time you just try to do several simplification and let theta, sine theta becomes theta. Sine theta becomes theta and cosine theta become 1 if theta is very small. So our equation can become to, finally will become to this one. So our natural frequency will be defined by the square root g over L plus 2k A2 over M L2. So we can define the spring turn or define the length to change our natural frequency. Or then we will try to see the example. This example will be if we have this kind of systems. What will be our governing equation? So if we treat like P as our pivot point here, so and we don't have mass turn, so we just have the summation, the tau should equal to 0. So this how do we do the so it will be the F multiplied L1. It will be the positive because it's rotate, it's this rotation, and the B turn. If we have a displacement along here, the damper turn will generate a force go to this direction. So it will generate a negative torque B dot Bx dot multiply L2 generate a negative torque. And the K, when we compress the stiffness, it will also generate a force along going down. So it will also generate a negative force. And then multiply the moment of arm will be the L2. So we will get Kx L2. We will get E should equal to 0. So our equation will be the Bx dot plus Kx equal to the L1 over L2 multiply F. So I announced the homework 1 in this week. It is Ohio collects submarines, and so we have a submarine, and we only consider the vertical coordination system. We don't need to consider we only consider the horizontal direction. We only want to derive the governing equation for I direction. We don't need to consider the J, okay? We only consider the governing equation for the I direction. And we have a drag force. Drag force will be related to the damper turn. It will be the damper coefficient multiply the velocity. And we have a propulsion force here, Fp, but I did not give you the propulsion force. I only give you the propulsion power. I only give you the power. So the power will be this curve. It will be the CV and the 1 plus EV. Then after a certain time, VC as T equal to TC, in this time, the engine will be closed, so the power will become 0. Okay. So what will be the free body diagram? Will be the first problem, and what will be the governing equations? So you need to give me a different ODE equations, the governing equations. And then you need to use the ODE to solve the problems. Okay, so to find the motion, Okay, and you need to use the Laplace transform to find the solutions. So it will be the analytical solution. You need to give me the analytical solution. It will be a lot of the parameter, not exactly number. And then the problem E will be what will be the velocity and the position. So this will be also the analytical solution. And then what will be the stop time? It will be also the analytical solution, certain equation with a lot of parameter. And then after the G, I will give you the table. So you need to replace the value from the table to get the numerical solution for the what is the pole, what is the residue. Residue is the coefficient. The coefficient for your after the partial fraction expansion. And what will be the shutdown velocity? What is the stop time? Shutdown velocity will be the VC. And then you need to plot the result in the MATLAB. Plot the velocity vs time and the power vs velocity. Then after H, we need to write a numerical solution. We need to write a Rock-Carter method. You can use 4th order, 5th order, 6th order, anyone is fine, but you need to use Rock-Carter. Oh no, it's not correct. You just need to use Rock-Carter method. Rock-Carter will be a certain order, okay? So use the Rock-Carter method to try to use the numerical method. You use the for loop to do the iteration to get the simulation result for the velocity to time, vs time. Okay, so it will be the result should be, you can compare this result with the Laplace transform result or ODE result. They should be very similar. And in this part, you cannot use the MATLAB function Rock-Carter. You need to write the Rock-Carter method by yourself. Okay, so I will teach you how to write the Rock-Carter in next week. So this after you understand how to write the Rock-Carter method, do the iteration to solve the numerical method, you can totally understand what is the simulation in when we use the ODE 45 and also in the Simulink. You will totally understand what happened inside the ODE 45. And the last part will be you need to draw the work and the energy from initial to the end. You need to draw the what is the proportional, what is the work done by the proportion, okay, force, and what is the kinetic energy for the submarine, and will be the energy dissipated by the jet force. So you need to and also show the balance of the energy. The balance should be the K summation of all of the input and output energy should be equal to 0. So you need to show me those kind of balance of energy. Okay.